NVIDIA containers, enabling GPU acceleration in containerized environments. Containerization has revolutionized software deployment and management, offering portability, efficiency, and scalability. However, as computational demands grow, particularly in fields such as artificial intelligence, machine learning, and scientific computing, the need for GPU acceleration within containerized environments has become increasingly apparent. NVIDIA containers have emerged as a solution to this challenge, providing a framework for seamlessly integrating GPU capabilities into containerized applications. NVIDIA containers are specialized software packages designed to enable GPU acceleration in containerized environments. At their core, these containers leverage the NVIDIA Container Toolkit, which includes a container runtime library, and utilities that facilitate GPU access within containers. The primary purpose of NVIDIA containers is to allow containerized applications to utilize NVIDIA GPUs with the same level of performance and functionality as native applications running directly on the host system. The key distinction between NVIDIA containers and standard containers lies in their ability to access and utilize GPU resources. While standard containers are isolated from the host's hardware resources, NVIDIA containers create a bridge between the containerized application and the host's GPUs, enabling high-performance computing tasks within the containerized environment. The NVIDIA Container Runtime forms the foundation of the NVIDIA container ecosystem. This runtime integrates with popular container platforms such as Docker, intercepting calls to the container runtime and performing the necessary actions to enable GPU access. The GPU pass-through mechanism involves mounting the required GPU device files and driver libraries from the host system into the container. This approach allows containerized applications to communicate with the GPU as if they were running natively on the host, without the need to install GPU drivers within the container itself. Driver and library management is handled dynamically by the NVIDIA Container Toolkit, which ensures that the appropriate versions of NVIDIA libraries and drivers are made available to the container based on the host system's configuration. This dynamic management maintains the portability of containers while providing optimal GPU support. Implementing NVIDIA containers requires a system with compatible NVIDIA GPUs and up-to-date NVIDIA drivers. The installation process typically involves adding NVIDIA's repository to the system, installing the NVIDIA Container Toolkit, and configuring Docker to use the NVIDIA runtime. While the specific steps may vary depending on the operating system and container platform, the general process includes installing the toolkit, updating the Docker daemon configuration, and restarting the Docker service. Verification of the installation can be performed by running a test container that executes the NVIDIA SMI command, which should display information about the available GPUs if the setup is successful. This testing phase is crucial to ensure proper integration between the container environment and the host's GPU resources. The applications of NVIDIA containers span a wide range of computationally intensive fields. In AI and machine learning, these containers enable the deployment of complex neural networks and deep learning models in portable, reproducible environments. High-performance computing benefits from NVIDIA containers in areas such as molecular dynamics, simulations and climate modeling. Scientific simulations, from astrophysics to fluid dynamics, leverage GPU acceleration through these containers to process vast amounts of data efficiently. In computer vision and graphics processing, NVIDIA containers facilitate tasks such as real-time video analysis and 3D rendering within containerized workflows. Performance analysis of NVIDIA containers generally shows that they achieve near-native GPU performance within containerized environments. Benchmarking studies have demonstrated that the overhead introduced by the containerization layer is minimal, often negligible in real-world applications. The ability to utilize multiple GPUs and scale across distributed systems further enhances the performance capabilities of NVIDIA containers, making them suitable for large-scale, GPU-intensive workloads. Despite their benefits, NVIDIA containers present certain challenges. The installation and configuration process can be complex, particularly in environments with specific security requirements or custom configurations. Some users report performance overhead, especially in scenarios involving frequent container creation and destruction. Compatibility issues may arise when dealing with different versions of NVIDIA drivers, CUDA libraries, and container runtimes. On Windows systems, there have been reports of high CPU usage associated with NVIDIA container processes, which can impact overall system performance. To maximize the benefits of NVIDIA containers, several best practices should be followed. Effective resource management involves properly allocating GPU resources to containers and monitoring GPU utilization to optimize workload distribution. Security considerations include running containers with appropriate permissions and regularly updating the NVIDIA Container Toolkit and associated drivers. Implementing robust monitoring and logging practices helps in identifying and resolving performance issues promptly. Version compatibility management is crucial, ensuring that the versions of NVIDIA drivers, CUDA libraries, and container images are aligned and compatible. NVIDIA containers integrate well with popular orchestration platforms. Kubernetes, coupled with the NVIDIA GPU operator, provides a scalable solution for managing GPU-accelerated containers in cluster environments. Docker Swarm offers native support for NVIDIA containers, allowing for the deployment of GPU-accelerated services across a swarm of Docker nodes. Cloud-based container services increasingly support NVIDIA containers, enabling GPU-accelerated workloads in cloud environments with minimal configuration overhead. The future of NVIDIA containers looks promising, with ongoing developments in GPU virtualization technologies that may further enhance the flexibility and efficiency of containerized GPU applications. Improvements in cross-platform support are expected to address some of the current limitations, particularly in Windows environments. Advancements in GPU sharing and multi-tenancy technologies may lead to more efficient utilization of GPU resources in containerized environments, potentially reducing costs and improving scalability. NVIDIA containers have significantly impacted the landscape of GPU-accelerated computing by bridging the gap between containerization and high-performance GPU utilization. They have enabled researchers, developers, and organizations to leverage the power of GPUs in portable, scalable, and reproducible environments. As containerization continues to evolve and GPU computing becomes increasingly central to advanced computational tasks, the role of NVIDIA containers in facilitating these workloads is likely to grow. The ongoing development of these technologies promises to further streamline the deployment of GPU-accelerated applications, potentially opening new avenues for innovation in fields ranging from artificial intelligence to scientific research.